Welcome to the lecture series on numerical methods, a finite difference approach. In the last lecture, we have discussed two-dimensional parabolic equations, and in the present lecture, we will start about these elliptic equations. So, in the elliptic equation, we can just find like two generalized equation. So, first equation it is called Laplace equation, and second equation it is called Poisson equation. So, if you will just go for this Laplace equation here. So, if we are just representing any type of parabolic equation, so then when it reaches like a steady state, since in two dimensional nature, whenever we are just dealing with this parabolic equations, so that is written especially in the form of del u by del t, this equals to del square u by del x square plus del square u by del y square. And if you just consider this system it is in a steady state, then especially we can just consider this del u by del t term as 0 there, and especially if you will just reduce this del u by del t term as 0 there, then this equation will be reduced to Laplace equation, and which is nothing but the elliptic equation of first kind, we can just say. And initial condition does not play any role in an elliptic equation, as the solution is fully dependent on the boundary conditions. And the most familiar elliptic equations are, as I have told, that they are Laplace equation and Poisson equation. Especially Laplace equation is signified as nabla square u, this is nothing but del square u by del x square plus del square u by del y square, this equals to 0. And if you will just consider f of x y in place of 0, so then we can just consider this as an Poisson equation here. So, whenever we are just defining this class of equations, so especially we should have to need like a domain where it should exist in the xy plane, and the appropriate boundary conditions are needed to get the solution along the boundaries, and especially the boundary is denoted here as C, and f of x y it should be known to us inside the domain. So, for solving this elliptic equations, so we subdivide the domain into rectangular mesh and discretize the partial differential equations at the mesh points. This leads to a set of like linear system of equations which can be solved either by Gaussian elimination method or by Gauss-Seidel method. Since in Gaussian elimination method especially we can just say that we will have a set of unknowns and we will have set of known values there, and in an iterated manner we can just get the solutions there. And in Gauss-Seidel method especially you can just find that some of this unknown values which can be known from the previous cycle of calculation, or some of this like n plus 1 time level of calculation, it can just take the immediate previous steps calculation values. And if you will just go for this solution of a Poisson equation here, so if you will just consider this equation which is written in equation 13.2 here, that is in the form of like nabla square u, that is nothing but f of x y, which should be defined over a rectangular domain D, where D is bounded between like x from 0 to a and y from 0 to b, with the Dirichlet condition u equals to uc, since in case of Dirichlet condition we have to prescribe u as the particular values at x equals to 0, y equals to 0, y equals to b suppose, and the mixed derivative condition, that is del u by del x equals to alpha u plus beta at x equals to a there. So, let the domain is subdivided into square mesh with side edge, that is we can just consider del x equals to del y equals to edge, so that your total size it will be represented as, or the total length in the x axis it can be just represented as mh equals to a, and in the y direction the total length from 0 to the last boundary of y can be represented as nh. And if each of these independent grid points we are just denoting it as like in the x axis as xi there, which can be written as ih, since I is varying from 0, 1, 2 up to m here. So, this 0 bracketed 1 m means the point will start from 0 incremented by 1 and it will move up to the point m there. Similarly, yj can be denoted as jh, where j is varying from 0 to n there. Then the mesh points ij corresponds to the point xi yj in the domain. So, if you will just signify in the domain here, then especially we are just writing x naught equals to 0, since your starting point is I equals to 0 here, then I equals to 1, then I equals to 2. So, likewise if we will just consider ith cell here, so then especially this node will be denoted as xi here, and its previous node will be like xi minus 1, and like foremost node is like xi plus 1 here. Similarly, if you will just go for y direction here, y0 or y naught equals to 0 here. So, this is the first boundary, and at the end we can just consider yn equals to b here, and if you will just consider a particular node point, suppose jth node here, then the particular value of y with respect to j node, it will be denoted as yj here, and its previous node will be yj minus 1, and this foremost node will be like yj plus 1, and this will just continue here 0, 1, 2, 3, likewise it will just go up to j minus 1, then j plus 1, then it will just continue up to yn equals to b there. Since in the boundary conditions it is prescribed that we will have like the Dirichlet condition u equals to uc along x equals to 0, y equals to 0, and y equals to b there, and we will have like a mixed derivative condition at x equals to a here. So, whenever we will just consider this mixed derivative condition, we require a fictitious shell, since if you will just consider the central difference scheme along this boundary here, it requires one more shell. So, after this boundary, so that is why we have just considered this fictitious boundary along this last boundary of x equals to a here. So, this subdivision, especially this just takes this grid sizes like del x in the x direction and del y in the y direction, or especially we can just signify this one as h likewise, and this one is since we are just considering here as del x equals to del y. So, we can just consider h equals to k there, or del x equals to del y. So, each of this direction, this is just this grid increments are coming in the form of like h size there. So, that is why we can just write here xi equals to x0 plus ih there, or we can just write xm, this can be written as like mh there, the total distance we can just say. Since the starting point is 0, then h, then 2h, 3h, so likewise if you will just move, so final point we can just get it as mh there. Similarly, if you will just go in the y direction, we can just find the last node point as nh there. So, if you will just go for this discretization of this Poisson equation there, that is nothing but we are just writing as del square u by del x square plus del square u by del y square, this equals to f of xy. So, we can just signify that one, this point as xi and yj points here over. But especially we are just denoting here, that is in the form of like u of xi minus 1 yj. So, that is why we are just writing this one as fij, or you can just signify this one as fij at this point here. So, if you will just go for the central difference approximation of this partial differential equation, the first term it will just give you like ui minus 1j minus 2 uij plus ui plus 1j by del x square plus order of del x square term, and plus if you will just go for the discretization of del square u by del y square, it can be represented in the form of uij minus 1 minus 2 uij plus uij plus 1 by del y square plus order of del y square here. And if you just neglect this higher powers of del x and del y here, or we can just neglect this error terms there over. So, we can just get this total expansion as in the form of like ui minus 1j minus 2 uij plus ui plus 1j by del x square plus ui j minus 1 minus 2 uij by del x square plus uij plus 1, this equals to nothing but fij here, since we are just denoting this one as xi yj there. And if you will just write del x equals to h and del y equals to h here, so obviously this del x square is nothing but h square and del y square equals to h square, and we have just write ui minus 1 j plus ui j minus 1 minus 4 ui j plus ui plus 1 j plus ui j plus 1, this equals to h square fij here. And if you will just take these values to be calculated at uijth level, so then we can just write uij at the unknownth level, that is at n plus 1 step here, which
which can be separated, and it can be written as like 1 by 4 if you just take to the right hand side here into ui minus 1 j, which is known from this previous step of calculation. Then if you will just see here ui j minus 1, which is also can be calculated, or it can be put from the previous step of calculation value. So that is why it can be written as n plus 1th levels here. But if you will just see here I plus 1 and j plus 1th level values, which is not known to us, that is why we can just put these values as ui plus 1 j n plus ui j plus 1 n, since it can be predicted, or it can be just put these values that as the previous step of calculated values here. So then if you will just see here minus h square f I j, which is already present there, so that we can just keep it in that form. And in this step, if you will just see that I is varying from 1 to m here, and j is varying from 1 to n minus 1. And this is specifically, if you will just see here at y last boundary, we are just using Dirichlet boundary condition. So that is why at nth step this value is known to us here. And if you will just see here y 0 at 0th level, so these values are also known to us. So that is why our computed value for j, it will just vary from 1 to n minus 1 here. So that is why if you will just see for I values, so I value it will just vary from 1 to m here, since we are just using a derivative boundary condition at the last boundary here. So that is why this last boundary value, it is not known to us. So that is why we can just vary these values, since x 0 value at 0th level, it is known to us initially, since it has been prescribed to us. So either it can be given from the initial conditions, or it can be calculated from the boundary conditions. So that is why this step of values, it is not known to us. So that is why we can just use this derivative boundary conditions that at the previous step and this fictitious step values, and then we can just evaluate this step at like mth position. So that is why this complete write off of this equation can be written in the form of like ui j n plus 1, this equals to 1 by 4 into ui minus 1 j at n plus 1th level plus ui j minus 1 at n plus 1th level plus ui plus 1 j at nth level plus ui j plus 1 at nth level. And this f of I j value, that is nothing but f of x I y j, it can be considered from this original equation, and it can directly put the values over here. So if you will just go for this further computations, taking the initial values of u, that is in the form of like ui j 0 equals to 0, varying from like I as 1 to m for a fixed j, and j equals to 1 to n minus 1. So each of this fixed I, we will just keep it off, and 1 by 1 j steps we will just move it off. This means that you can just see that whenever we will just go for the calculation here. So first step I equals to, for j equals to 0 here, all the values of I is known to us. But for the further calculation, if you will just go for like here like del y increment here, so then all this calculation for fixed j, it will just move for this cycle here. So that is why this I will vary for a fixed j, again this j will be fixed, again this I will be vary at these points. So likewise the computation will proceed, or the calculation will be proceed. So if you will just consider this boundary conditions there in the formula 13.4, especially if you will just see here. So 13.4, it requires like I minus 1, and one more point if you will just see here I plus 1 and j minus 1 and j plus 1 here. So that is why we can just consider this boundary on the prescribed point, that is x equals to a, can be approximated, since we are just using the central difference approximation here, which gives this like order of approximation as order of h square here. So especially we can just write this last boundary, that is in the form like since xm is the last boundary here, so that is why we are just writing u m plus 1 j minus u I minus m minus 1 j by 2 h, this equals to alpha u m j, since this is the particular point alpha u plus beta. So and where this u m plus 1 j value, this is the fictitious cell value which is not known to us. So which can be updated by considering this u m minus 1 j value, which is existing inside the domain there, and which can be just added whenever this value will be computed from this previous cycle of calculation.
If you will just go for a practical problem here, so this problem if we are just considering here as like del square u by del x square plus del square u by del y square, this equals to 0.5 is defined over a rectangular domain, where this domain is defined within the range like x is lying 0 to 0.6 and y is lying between 0 to 0.6 with boundary conditions u equals to 1 at 3 sides, x equals to 0, y equals to 0 and y equals to 0.6 and del u by del x equals to u on x equals to 0.6. And the question is asked to solve this equation by taking h equals to 0.2 and approximating the derivative boundary conditions by a central difference approximation. Since the question is given, this boundary is existing like in the form of like x equals to 0 to x equals to 0.6 and y is starting at 0 to 0.6 here. So, this is a closed domain and the boundary conditions it is just written in the form of like 3 sides x equals to 0 and x equals to like 0.6, we have like here del u by del x equals to u and at y equals to 0. So, this boundary we can just consider as this one as u equals to 1 here and this one u equals to 1 and this one u equals to 1 here. So, if you just see, since this derivative boundary condition it is just given along x equals to 0.6 here or at the last boundary, we can just consider the central difference approximation along this boundary as, since if you just see here that h equals to 0.2 if you just consider. So, we can just move like 0, 0.2, then 0.4 and the 0.6 and we have to consider one fictitious cell here. So, which will vary like one more extra point here. And if you just see here, j will vary from like 1 to only, since the last boundary, first boundary is 0 here. So, 0.2 then 0.4 and last is 0.6 here. So, that is why j can be vary from only 1 and 2 points and I will vary from like 1 to 3 points here, since 4 is the fictitious boundary which can be just updated from this previous step values. And if you just approximate this derivative boundary condition at this last boundary here, so the last boundary it is just represented at x equals to 4 there, or we can just consider this one as 0.8 here. So, that is why this cell can be considered as like u of 4 1 minus u of 2 1 by 0.4, this equals to u 3 1. Since we are just considering this one as like last boundary, since we are just considering for y equals to 1 here, or you can just denote this one as u of 4j minus u of 2j by 2 into h here. H is given as 0.2, that is why it is just taken as 0.4 here, which can be represented as u3j here. So, if we will just move in that form, then we will have this domain structure like this one. So, here I have just denoted as in a clear form x equals to 0.0 here and the starting point is x equals to 0.2 and incremented by 0.2, that is why second is like x equals to 0.4, third is x equals to 0.6 and this is the fictitious boundary here. And j is also varying like j equals to 1, that just takes the value like y1 equals to 0.2 and y2 equals to 0.4. So, last boundary y3 equals to 0.6 here. And if you just varying this boundary, j is a variation here. So, we can just write like u41 as u21 plus 0.4 u31 here, then u42 this can be written as u22 plus 0.4 u32. Since if you just see here, so we have just kept it as 0.4 as the division form and we are just taking this one in the right hand side as a multiplied form there. And discretizing this partial differential equation at various mass points like ij, I is varying from 1 to 3 and j is varying from 1 to 2 here. Then we can just find this discretized value as the first one. If you just see here, we will have like a ui minus 1 j plus ui j minus 1 minus 4 ui j plus ui plus 1 j plus uij plus 1, this equals to h square fij. And if you just consider like starting point is suppose I equals to 1 here and j equals to 1. So that's why if you just separate this term here, that is in the form of uij n plus 1, which is written especially in the form of 1 by 4 ui minus 1 j power n plus 1 here, plus uij minus 1 power as n plus 1 here. So plus ui plus 1 j power n here, plus uij plus 1 power n here, minus h square fij. So if you just multiply 4 in this side, so we can just write this one as in the form like 4 into uij plus uij to the power n plus 1, this can be written in this form here. And since I equals to 1 here, j equals to 1, especially 4 u on 1 and I minus 1 means we can just write 1 minus 1, this is 0 here, and j is 1 here, then ui 1 is there, j minus 1 is just taking 0 value here, then u2 1, since 1 plus 1 this is 2, and j is 1 here, then u1, j plus 1 means 1 plus 1 this is 2 here, minus h square f11 here. And whenever we will just consider like h equals to 0.2 here, so we will have like a fij is just defined as 0.5 here. So 0.5 if you just consider into 0.2 into 0.2, especially we are just considering. So that's why this value is coming as 0.02 here. And for all ij, therefore we can just write this one as a u11 to the power n plus 1, since this left hand side is unknown here. And first to u01 and u10 especially if you just see, so then you can just find that u01 we can just consider, since 0 is the like I equals to 0 is the this boundary here, 01 it is just prescribed as 1 value, u equals to 1 is given here. And if you just see 1 0 also, this is just given the value as 1 there. So that's why 1 plus 1 this is 2 here. So 2 minus this is like 0.02. So that's why this is just given as 1.8. So if you just put these values here, especially I can just write this one plus 1 minus this is 0.02. So that's why this just gives the value 1.98 here. Similarly, if you just go for like is 2 1 cell here. So since we are just varying like I fixing j there itself, so that's why I am just keeping fixed j here. So j equals to 1 only, and I is varying like 1 2 3, so likewise it will just vary. So if I will just go for this 2 1 cell here, I can just find here as, if you will see here this formulation here. So this means I minus 1, this is nothing but 2 minus 1 is 1 here, then 2 here, then j minus 1 means 0 here, then u of 3, 2 plus 1 this is 3, then 1 here, plus u2, and this is j plus 1 is 2 here, minus h square f21 here. And 2 0 especially if you just see, this means that j equals to 0 here, j equals to 0, if you see this boundary condition is fixed as u equals to 1 there. So that's why this value is 1 minus this value is like 0.02, so that's why this 0.98 it is coming, and all other values are unknown to us. And this u11 value we can just predict it out, since u11 it is computed from this previous cycle here, so this can be put it there for the next operation. And if you just go for I equals to 3 there, keeping fixed j there, so we can just have this series expansion as in this form here, 4u31 this equals to u21 plus u30 plus u41 plus u32 minus h square f31 here. And if you just see here u30, if you especially if you just see here, so this is nothing but j equals to 0 means this is u equals to 1, and this is nothing but you can have the value like 0.02. So that's why this difference is coming as 0.98 here. And if you just see here u41 cell, so that is nothing but if you will just go for our previous calculation, u41 is defined as u21 plus 0.4 u31. So which is just determined in the form of u21 and u31. So that's why we have like a 2 u21 here, and if you just go for like a one term added it over here for u31, so that can be taken to the left hand side and which can be eliminated directly and which has this formulation here. So especially u41 is replaced by the central difference scheme. And finally, if you just go for like u of 1 2 here, that is keeping j as 2, since j computation for like 1 we have completed, so that's why we are just moving one more further step for j. So if j equals to 2 for I equals to 1 here, so this can be written as u4 of u12, this equals to u02 plus u11, u22 plus u13 minus h square f12 here. So if you will just see here, this means that j equals to 3, we will have this boundary condition u equals to 1 there, and we will have like u02, we will have u equals to 1. So that's why 1 plus 1, this is nothing but 2 here. So 2 minus this is 0.02, so that's why this is just giving 1.98 here, and the rest of this can be updated from this previous cycle of calculation or from the known values. So u11 n plus 1, it is known to us, so that's why we have just written it as n plus 1 here, and this is unknown to us, so that's why we have just written it as n form here. Similarly, if you just go for like I equals to 2 for a fixed j equals to 2 there, so then we can just represent this equation in this form here. For j equals to 3, these values is known to us, u equals to 1, so that's why 1 minus 0.02, so that is nothing but 0.8 here. So all other, if you just see here, 1 2, 2 1 and u3 is 2 is there. So these values are known from this previous steps, whatever we have just made it now. So this can be updated from that step values there. And next, if you just go for I equals to 3 here, so this can be written in the form of like u22, u31 plus u42 plus u33 minus h square f(ij) here. So if you just see here, for j equals to 3, we will have this known value there. So that's why 1 minus 0.02, so that's why this is just giving you 0.98 here, and u42, if you just see, this can be replaced by the central difference approximation, and where this u22 it will just come, and u32 it will just come over there. So u32 it can be separated out in from the one term from the left hand side, and u22 can be joined here as 2u22 here. So if you just solve this above set of equations by substituting these most recent values of u, the convergence is achieved after 14 iterations. The iterated values we are just denoting here. Since I is varying like 1, 2, 3 here, for a fixed j, we can just iteratively get all these values here. So if you just see here, like repeated values are obtaining like 1.0137 here and 1.0142. So after like third decimal places, this convergence is occurring. So that's why we have just considered this one as the last iterated value here. And by considering these values, again we are just moving for the second iteration, and we are just getting from these two steps that this difference is just minute here. This means first step we are just getting 1.0142, and from this second cycle of calculation we are just getting this one as the last values here. So that's why this just shows this convergence rate for this Gauss iterated methods. So if you will just iterative values are shown in the table after skipping the alternative iterative values, if you just consider here, then you can just find that this updatation of the values you can just predict out from this table here. So whenever we are just going this tabular values calculation here, in each of these I step values, if you just see here, so 0.495 minus 0.8642, so likewise if you just go, so finally we can just find the difference of 1.0137 minus like 1.0142 here, the differences here. So then we can just find this convergence rates. So if you just visualize, so this convergence is coming up to third order here. And similarly, if you just go for these steps, you can just find this difference is coming up to third order also there. So after this we can just conclude that this is the convergence iterated values for like these variables here. Thank you for listening this lecture.